Well, welcome everybody, and we want to thank Avemco for sponsoring this series of webinars, and I also want to thank my colleague Layne Lisser, who is here engineering for us and monitoring the chat. Today we have a special guest presenter, Kurt Kleiner. You see the screen and there's image in the middle there. I'm Gene Benson, and I'll be your host today. This event is being recorded and will be available on my YouTube channel within 4 hours after we end the webinar. In case you didn't know, Avemco is the sponsor of the phase of the wings that we see when you complete a phase of wings. At the end of this presentation, I'll tell you how you might be eligible for a discount on your aircraft repairs for attending the webinar. So stay tuned for that. Let's start with a bit of housekeeping. Live seminars, we tell you where the bathrooms are and where the exits are. That in your location. And our emergency crash at my end. It's unlikely, but if it does happen, check your email or go to vectorpeoplesafety.com for try again. All right, I want to welcome our guest presenter today. Kurt Kleiner has been a CFI for 15 years. He got about 3,700 hours of year given and 4,200 hours time on airplanes, sailplanes, seaplanes, paragliders. He's retired from a 29-year career as an aviation manager with the Bureau of Land Management for the U.S. Forest Service. Much of the focus he had was on instructing human factors, risk management, and CRM for firefighting aircrews. For the last 2 years, he was the National Airspace Program Manager and was focused on refining our federal Land Management Agency airspace coordination policies and procedures manual and teaching agency fire managers and dispatchers how to design, modify, and implement the PFRs for the hundreds of summertime wildfires in the West. Presently living in Montana, Kurt is a mountain flying enthusiast and is very knowledgeable on the subject. So at that point, I'm going to turn this over to Kurt. I'm going to be the presenter.
Okay.
And there you go, Kurt. You have it.
Okay, very good. Minimize this and get back to my... All right. Can everyone see the title slide now?
I'm seeing it, and I'm going to stop my webcam at this point.
Okay.
I can see it.
All right, thanks. All right, well, thanks for that introduction, Gene. And we're going to go ahead and look at the objectives and our briefing topics for today. We're going to talk about some of the atmospheric conditions needed for wave to form and the structure of mountain waves, different types of mountain waves, and how we can look at some weather products to predict if we have wave and how strong and where it might exist. As pilots, always doing self-briefing on weather before we fly. We'll talk about some of the specific hazards to aviators and some of the soaring techniques and some of the state, national, and world records that have been set for altitude soaring and wave. Wave soaring has been pretty popular here in North America since back in the 50s, and there have been some incredible flights accomplished, and we'll talk about a few of those. Okay, the information sources, this is just a snapshot of one of many books about mountain meteorology. It's got a nice photo of some mountain wave clouds there over a mountain there. This advisory circular is a great resource. It's actually published back in 97, so it's actually old and relatively old, but it's still very thorough and valid, and all the information is really good. Also, the Soaring Society of America, most soaring pilots, glider pilots are members of that, and there's lots of soaring websites. One in particular I recently discovered that has some great tutorials is the YouTube channel by a guy named Fred Remer, or Remer, R-E-M-E-R. And if you go to his YouTubes, you can learn a lot more about some of the topics we're going to talk about today. So another great resource online. And then, of course, if you're technical minded or you're a meteorologist, these are some organizations that have some very in-depth technical information that makes me scratch my head on the science behind mountain waves. So, okay, so moving along, 3 necessary conditions for wave to form. Basically, there's 3 components: the wind, the topography, and the atmospheric stability. So generally speaking, and a lot of things I'll say today are general in nature. There are always exceptions or slight differences from time to time. But generally, you need a wind 20 to 25 knots or stronger at mountaintop level. And you need a mountain range that is generally aligned perpendicular to the direction of the wind flow. So here in North America, most of our mountain ranges in the west are aligned north-south. You look at the Tetons, the Wasatch, the Sierra Nevada, the mountains up here in Montana, generally speaking, run north-south. When we get prevailing west or southwest or northwest winds, any wind speed that's strong and hitting the mountains range broadside has the potential in some situations to create mountain wave. Now, we do have peaks like Mount Hood, Mount Rainier, Mount Shasta, up and down the Cascades on the west coast, where you might have a lone volcano like that sticking up much higher than all the surrounding terrain. In that case, when you have a lone peak like that, you can get a wind from any direction. It could be a north wind or a south wind that's pretty strong, and you still might get wave creation off of a single high peak like that. So, atmospheric stability, yeah, especially on the downwind side, the atmosphere needs to be fairly stable, and I'll explain why in just a second. But if it were unstable, for example, you had a lot of convective up and down motion in the atmosphere, any wind with moisture that's coming onshore and striking the Cascades, for example, or any wind that's pushing moist air up the west side of the Tetons or the Wasatch Range in Utah, if it's unstable, it's going to result in towering cumulus clouds like we see in the summertime, mountain thunderstorms in the late afternoon like we typically see. So in order for wave to form, it has to be fairly unstable and resistant to vertical motion, and especially on the downwind side. So if I were to be asked by, say, a student or somebody who wasn't an aviator, what is this mountain wave you're talking about? How does it work? This would be like a generic discussion or description of how it works that I would give. Basically, you get the strong upslope flow of stable air up and over the top of the mountain, and it's compressed. And because it's stable and the lapse rate is relatively stable, it wants to go rushing down the lee side back to its equilibrium where it started from. It doesn't want to continue up in a convective manner. So it rebounds off the stable layer below on the lee side, and it bounces back up and down and up and down and up and down. And when I do this presentation in a classroom, sometimes I'll take a tennis ball and I'll throw it across the room and say, see how the tennis ball, boom, you know, it bounces across the floor, and each bounce gets a little bit shorter, and then it eventually dissipates, but it wants to return back to equilibrium. So typically we know as pilots, or we learned, that a visual indicator of mountain wave are standing lenticular clouds, typically called Altocumulus, Lenticularis. Up at higher altitudes, you can get cirrocumulus, Lenticularis clouds. So this photo is taken actually from my driveway looking south down the Bitterroot Valley. The mountains are to the right, to the west out of the photo, and you can tell that the wind, and you can see my little cursor, right, moving? You can tell that the wind is out of this direction because these rotor clouds come up and curl around. You can see them curling like that. So here you have the leading edge of the wave, and then the trough, and a secondary wave. Glider pilots typically would call this the primary wave, the secondary wave, and out of the photo to the left would possibly be a third or fourth wave, showing where the rebound bounces up and down off the stable layer of air below. Okay, One thing in particular, we're going to talk quite a bit more about it, is these rotor clouds. These are the primary hazards to aviators. If you're flying around up here at the higher altitudes on the leading edge of the wave, you might get really strong lift, or you might get strong sinking air, but it's going to be relatively smooth in these areas. It's the rotors that you really want to look out for. We'll talk more about those. So here's another diagram of the mountain wave. Here you can see the primary wave, the lenticular, that forms just above and slightly downwind of the peak, and then the next rebound, and the rotor is typically found underneath. Now, as pilots, we're always taught, especially in all these mountain flying courses and online tutorials on mountain flying, they say, don't fly on the lee side of ridges, don't fly at low altitude in the mountains on the back of the downwind side. And what they're talking about are the terrain-induced rotors in this area. And indeed, yeah, that's a major hazard. If you have a underpowered aircraft and you're flying at high density altitude on a summer day, maybe you have 160 horsepower Cessna 172, and you're maybe able to get at VY with max power 300 to 500 feet per minute of climb, and you fly into a 800 to 1,000 foot per minute downdraft, and you're only at 500 AGL. That's where you get problems with lots of aircraft accidents in the mountains historically at low altitude, just on the lee side. That can happen whether we have wave lift or not. Anytime there's terrain and wind, even if it's convective, there is going to be some spillover and downdrafts and rotors right above the terrain. So in the context of mountain wave, when we talk about rotors, we're mainly talking about the rotor that's underneath the crest of the wave where the lenticulars are, and you might be miles and miles away from the terrain, way out over the flatland, so you can still get these rotors associated with the wave. Okay, so here's a diagram. People sometimes go, well, why does the cloud not move? If the wind is honking at 30, 40, 50 knots over the mountains, why are the clouds stationary? And simply, you think back to Weather 101 when we were brand new student pilots, and we learned that in order for clouds to form, the moisture that's in the atmosphere has to cool to the dew point level, and it does so by blowing up slope. And as the wind blows down, that temperature dew point spread opens back up, and the ability down here for clouds to form is non-existent because the temperature dew point spread is opened back up. So the wind is basically blowing through the lenticular clouds, and the next one would be over here. Now, if you don't have enough moisture in the atmosphere, you can get wave conditions with no visual indicators. So you can have dry wave in very dry atmospheric conditions. Catch up and move on here. Okay, yeah, when we talk about wave structure, we refer to wave length and amplitude. So the length would be from the top of one crest of the wave to the next crest. And we're going to talk about different conditions, some which have amplitudes that are very steep up and down and very short wavelengths, and other conditions that create really wave crests that are far apart. When we talk about amplitude, we pick the midpoint between the trough and the crest. And if you drew a line right here, just like this arrow shows, that would be a measure of the amplitude. So that's what those terms mean. And of course, here's your lee side terrain-induced rotor shown in this one. Okay, so what does determine how long the wave length is? Generally speaking, the stronger the wind, the longer the wavelengths are, and the shorter the altitude. Now, of course, there are exceptions depending on other circumstances, but that's a general statement. And then the slope angle and the height of the mountain's lee side. So if you get a range of mountains like the Tetons or the Sierras, where you have 7,000, 8,000, up to 10,000 foot change in elevation from the tops of the peaks down to the valley floor on the backside, you might get really steep flow of downsloping air that rebounds off the valley floor and springs back up because of the force and the great distance of that lee side. You can also get wave, say, in the Appalachians, and we'll look at some photos of that shortly, where the lee sides are generally shallower slopes. So doesn't mean you can't get wave, it's just that you're not going to get a major amplitude, and you'll probably get longer wavelengths out of wind hitting a range like that. In some conditions, the wavelengths from one to the next crest can extend up to 500 miles or farther downwind. If there's any airline pilots on this webinar who have ever flown out of Denver, say in the fall or winter, you've probably experienced mountain wave that can extend off the Rocky Mountains all the way across eastern Colorado, all the way across Kansas, all the way to the Missouri state line, or even further. So that's an example of mountain wave off a range with really strong winds aloft that can extend for a long, long ways downwind. So typically, this is another generic, generally speaking, you know, the 8 to 10 miles apart is pretty typical for the distance from one wave crest to the next. But they could be shorter, they could be farther. Okay, another fact about amplitude. So again, the steep slope on the lee side, and I basically already addressed this upper part. The stability needs to resist convection for the most part. If there's a lot of instability and thermal activity and convective activity on the lee side that's producing a lot of up and down motion, even if you have strong winds going over the top of the mountains, that's going to kill the ability for any wave to form. Now, there's a caveat here because soaring pilots often need a little bit of instability, certainly some solar heating, some thermal activity that isn't too powerful in order to work the lift on the lee side to get up and catch the wave and start soaring up from there. So if there is some instability, it won't kill the wave outright, but if it's really strong instability on the lee side, it can. So this last statement here in the bullet, amplitude can be re-energized by terrain downwind. Here's an aerial photo of western Montana. This is the Mission Mountains. This area is called the Swan Valley. It's northeast of Missoula, Montana. And this is the Swan Range. So suppose we're getting wind out of the southwest where my cursor is moving. It springs up and over, and you got wave conditions. It's rebounding. It hits the next mountain wave or the next mountain range, and it re-energizes that wave, a lot like exhaust air going through a turbocharged engine. That's a good analogy. It re-energizes it, and then, boom, it's strong again. It never really dissipates until it's over this last mountain range and out over the Great Plains, over by Augusta and Choteau and Great Falls, and on the east side of the Rockies. And so you can get massive wave forming in this area because it's been energized 3 or 4 times by jumping up and over multiple mountain ranges. So amplitude, let's talk about that. Here's a photo of some wave. Remember I was saying it forms mainly on the downwind side. So here you have wave coming up and over the Sierras, over the Holmes Valley, rebounding up and over the top. Normally, the greatest amplitude is found 3,000 to 6,000 feet above mountaintop level on the downwind side, but there can be strong wind at higher altitudes too. We'll look at that in just a minute. And then the greater the amplitude, when you have a certain condition we'll talk about called vertically propagating wave, a lot of times there may be 1 or 2 massive wave crests, but then it dissipates. Downwind, it doesn't extend that far, but it's very powerful immediately downwind of the mountains. So this is looking south on the Owens Valley, on the east side of the Sierra Nevada range. By the way, the tops of the peaks in the Sierras, a lot of them are 12,000, 13,000. The highest peak, Mount Whitney, is all the way up to 14,000. The valley floor down here at Bishop and Lone Pine and those towns, it's only 4,000 feet. So you got a 10,000 vertical foot drop for that wind to flow up and over the Sierras, and a lot of power when it rebounds up off the Owens Valley. And that's why the Owens Valley is actually one of the best places in the world for soaring in mountain wave. A lot of Europeans and folks from Japan come here in the winter to get their personal best altitude soaring flights. So it's a very popular place for soaring, and for good reason. So here's an image that I got from these researchers, Sheridan and Vosper. It shows some amplitude plots of a radiosonde-based computer model, radiosonde being weather balloons that are sent up to give us winds and temperatures aloft. And this computer model is showing in the right-hand side meters per second. So where it's brown, yellow, brown, and dark brown, that's really strong lift. And where it's green or blue or purple is where there's sink. So here it shows the Sierra Nevada mountains, a profile looking to the north. This is the Owens Valley down here, and this would be the White Mountains across the Owens Valley on the east side. And these are the mountain ranges right about where the Nevada state line is that extend over into Nevada. So around the towns of Austin and Tonopah and all the way over to Ely, you have multiple mountain ranges. So here you can see strong sink right where the downslope is, but it rebounds when this air hits the stable air layer on the lee side, springs back up, and you get some higher altitude wave right here also. Then, of course, on the back side of the wave, you get sinking air, rising air, sinking air. So this is where the best lift is. And if these peaks right here are 12, 13,000 feet, yeah, this is where your strongest and your best soaring is going to be, right in these steep climb gradients right here. So, okay, sometimes you get stacks of lenticular like this. We're going to talk about the different types of wave, starting with the vertically propagating wave. So a vertically propagating wave occurs when the air flows up and over and it rebounds at least once down the lee side, but then it kind of tapers out. Here you can see where the lift and starts leaning back. The crests of the wave actually lean back upwind a little bit. They tilt. And you can see the stack of lenticulars are actually tilting back more upwind in a vertically propagating wave. So this kind of wave, you can get some really good high altitude flights in sailplanes. And in some cases, you get really strong, severe air, clear air turbulence at these higher altitudes. These are, now we're up here looking at the 18 to 25, 30,000 foot level. Down here, we're talking about 15 to 18,000 feet. So we'll talk a little more about that. Sometimes vertically propagating wave will actually break. And notice the tilt back angle is even greater, and you get what's called a hydraulic jump, where this air is compressed and it springs back off and it actually curls back around, boom. And this is the kind of condition that you get PIREPs you see for clear air turbulence, severe turbulence, way up at the flight levels where the airliners are. And of course, here is the lower altitude, you get the primary wave, a good jump, a lot of great lift here, but then it kind of dissipates out. So we'll talk here in just a second about why does this dissipate out and not extend with multiple crests and troughs going downwind. I'll catch up real quick here. So looking at some of these other bullets underneath here, yeah, the amplitude is so severe that it actually breaks. And so if you don't get breaking wave and you just have vertically propagating wave, you might get strong lift and sink, but your main hazard to aviation is still going to be in these rotors, more so than at that clear air turbulence. And you can get a lot of turbulence in this area. So even if you're not flying directly in the rotor, you'll get a really strong updraft. So you have to be prepared for that when you see vertically propagating wave with stacks of lenticulars that look like a stack of pancakes going up. Here's another diagram, same diagram. This shows where the breaking wave would occur at the higher altitudes. Okay, and this is another diagram that really shows this jump. And I guess the best analogy when I think about the wave striking the ground and curling back up and breaking over is best described by these photos. You can see these raptors getting flipped up and completely backwards because they're literally in the exact same kind of hydraulic jump that this wave is producing in the atmosphere, but on a much smaller micro scale, just in that hole around the backside of the wave in the river. So yeah, it doesn't look like a lot of fun getting tossed out in that water. Okay, the other kind of wave, and this is actually more common, is the trapped lee wave. You see this a lot over in the Appalachians and smaller mountain ranges. Here you get the wind striking the mountains, and it rebounds up and goes down and up and down and up and down, and you get several bands of wave. And notice that it doesn't propagate vertically. It's basically weaker at higher altitudes. So let's talk for just a second about some of the factors that causes the wave not to propagate vertically as much. So usually the main factor is the wind shear aloft. So if the winds aloft are significantly stronger at 18,000 feet than they are down at 9,000 and 12,000, like twice as strong, for example, that wind aloft is going to shear off the top of any amplitude that may be wanting to form, and it's going to flatten out that wave with stronger winds aloft. Now, if the winds aloft at 12,000, say, are 35 knots, and up at 18,000, it's 38 knots, very little difference in speed. And if the direction isn't different by more than maybe 10 or 20 degrees, sure, you could get high amplitude, vertically propagating wave in those conditions. So it's really about the wind shear aloft will determine whether you're going to get trapped lee wave or vertically propagating wave. So they call it trapped because that wind shear aloft suppresses the amplitude from going up very far, and the air that's going up and down has the ability to bounce and rebound back and forth. So if I were in a classroom or something and I had my tennis ball and I was going to bounce it across the floor, I would set up a couple of large tables, and I could show the class that, hey, I'm going to stand right next to the edge of this table and throw my tennis ball onto the floor, make it bounce up and hit the underside of the table, and it's going to trap that bouncing ball from going up any higher than the underside of that table. So it's the exact same physics at work here in the atmosphere. So a lot of times, you know, the rotors will be less severe than they would in a really high amplitude wave situation like vertically propagating. So your waves, your rotors still could be a hazard to aviators, but they're not always quite as strong as the ones found when you have hydraulic jump like we just saw. And again, they can extend much, much further downwind than a vertically propagating wave typically. So here's an image looking up at the satellite photo. That's the state of West Virginia in the Appalachians. And look at all these bands, one after another, all the way across the state of Virginia for a couple hundred miles. From a glider's point of view, the photo on the left kind of shows what that would look like. Notice you don't have a stack, a very tall stack of multiple lenticular clouds. It's not like the ones you sometimes see that are saucers that are stacked one above the other. They're pretty flat down below, but that wave is extending a long distance because it's trapped lee wave. Trapped lee wave is actually a little more user-friendly for glider pilots who are just learning how to fly in mountain wave and how to work the altitude. It's usually not nearly as severe as a large amplitude wave, so it's not quite as intimidating. So how can we predict or forecast waves? So these are the equations that are used by atmospheric physicists to determine the eddy dissipation rate. So over the next hour or so, we're going to break this equation down by all the certain elements and describe exactly how to derive the solution to this equation. No, I'm just joking. We will not be doing that. But thank heavens we have the National Weather Service that captures that equation and the results of it right into one-stop shopping at aviationweather.gov. When you go to the website, just click on forecasts right here at the top in this white band, and then a box will open up and you go down about 3 lines and you click on turbulence. Boom. Look at this. It just gives you the same image, and it also tells you eddy dissipation rate given in a color shading. So again, the darker reds into dark brown is strong mountain wave. Here we show some mountain wave just on the east side of the Rockies here in Montana, and also just on the east side of the Tetons in Yellowstone right here in Wyoming. And I captured this image from Aviation Weather on the same day that I observed some pretty major mountain wave going on right here in the Bitterroot Valley. And I said, here's a great opportunity to see what the weather products look like that validate what I'm looking at. So I went to the winds and temperatures aloft. Here's the winds at GPI, that's Glacier Park International. That's one of the winds aloft reporting locations in Montana, up at Kalispell, just on the west side of Glacier National Park. Here at 9,000 feet, wind 290, 37 knots. Here at 12,000 feet, winds 290 at 47 knots. Here at 18,000, 290 at 42, drops down a little bit. So you can see that the wind, the higher you go, really isn't that strong. So just looking at these numbers, I know that if I'm having wave conditions that day, it's going to be a vertically propagating wave, because this number here would have to be way up like 55 or 60 in order for that wind shear condition to exist that would shave off the top of the amplitude and relegate that wave to a trapped lee wave. So again, if the wind speeds at altitude aren't that different from the lower altitudes here, that's when you're going to get vertically propagating wave. So this is another great indicator. And the other phenomena that I noticed on that same day, here we have high pressure. So we got very stable atmospheric conditions. That's what you need for wave to form. Here we got a high. If you can imagine, the rotation of air around a high is clockwise, and it usually goes out also. So as it circles around, it tends to expand out. What we have going on here are 2 high pressure centers, one over here. Any of the wind that's going out of this high pressure is then boosted or turbocharged by this high pressure, and bam, it goes right across the Rockies with the force of both barrels of the shotgun right across the Rockies in western Montana. And sure enough, look at this, the isobars here, we're showing a major temperature gradient here, really strong winds indicated by isobars when they're packed close together, as we learned. So this is another validation or verification as to why we're seeing strong mountain wave on this particular day. Again, I looked at air mets. That's another one. Say, okay, we got a air met for turbulence at the lower altitudes. Top is only 16,000 feet in this case, but moderate turbulence. As we know, turbulence could be caused by, cold fronts, or it could be caused by any time you have terrain-induced wind and terrain, and you have low-level turbulence. But in this case, this turbulence was caused by the mountain wave. A lot of times you'll see, when you pull up the clear air turbulence, you'll see, like, for example, if this shaded area of strong clear air turbulence was over the east side of California into Nevada, you go, aha, that's part of what's contributing to this condition that's forming the high winds flowing up into the mountains and the formation of mountain wave. On this particular day here in Montana, clear or the winds up here were the jet stream, I should say, being at lower altitude was not a contributing factor. This is the jet stream map. It was not a contributing factor on this particular day, but those other aspects, the two high pressure centers, the isobars being close together, and the perfect winds aloft are what created the mountain wave. Did not have the jet stream near us on this particular day. Okay, and then again, if you want to learn about, if you suspect there's strong mountain wave, look at the SIGMETs and AirMETs. Here's one that they specifically say, due to mountain wave activity. This one is base 24,000, the top of 33,000 feet. I would guess, because we're looking at these higher altitudes for this SIGMET, that this is a vertically propagating wave that's a breaking wave causing this much severe turbulence at higher altitude. Here's a low level, 0 to 12,000 feet, another SIGMET. Due to strong low level winds and wind shear, that's primarily rain induced. So you look at all aspects of the weather when you're doing your self-briefing. Here's a PIREP submitted by a Boeing 737, moderate to occasional severe turbulence, 25,000 feet. This was, again, in mountain wave conditions on a completely different day. This was not the same day we had wave in Montana. So this aircraft was westbound and encountered this severe turbulence associated with mountain wave. Okay, the SKU-T log P chart. This is a great tool for all kinds of purposes. You can predict and validate where there's going to be mountain wave. It's also great for determining if you're going to get icing conditions, if you're going to get convective activity in thunderstorms. You can use this chart to determine where the cloud base is. On the right-hand edge, it shows wind barbs that show the strength and direction of your winds aloft at different altitudes. These are all given in millibars. So you have a lot of information in this one product that's, I think, very underutilized by pilots. However, it does take some practice and some study to really understand and learn how to use that chart. But it's a great tool. If you can take the time and do a tutorial online and learn how to use the SKU-T chart, it will really teach you a lot about atmospheric conditions. Okay, do we have any questions so far, Layne, from the chat?
Nope, nothing so far, Kurt. We're all just kind of watching with our eyes open.
Okay.
Hey, guys. I was monitoring the questions here, and there are a number of questions in the Q&A area as opposed to in the chat.
Okay.
Can you see that one?
I am not seeing any questions showing up there. Let me do this.
We had some earlier about audio quality, but I think that was because I had my microphone was not muted. Well, Layne tries to find where the questions are there. It's in the main menu there. I'll go ahead and read a couple of them if that's okay.
Sure.
This one says, how far above the ridge level would you need to fly to be above any significant mountain wave effects?
That is a great question. We actually have some slides coming up with that exact answer. So I'll give you the sneak preview. So generally speaking, you look at the elevation of the base of the mountains and the top of the mountain. So let's say you had 8,000 foot drop from the summits down to the valley floor. You want to be above the mountaintops by at least half that. So let's say the top of the mountains are at 8,000 feet. And if the base of the mountains are down at, say, 1,000 feet, that's like 7,000 feet. You'd want to be at least 3,000 to 4,000 feet above mountaintop level, 1.5 times the altitude of the vertical drop of the terrain. That's a good rule of thumb.
Okay, thanks, Kurt, and we'll look forward to those slides coming up on there. Here's another one. Does the rotor cloud always rotate back toward the mountain in a clockwise or counterclockwise motion?
That it doesn't, it curls up and around and back towards the mountain, but once it's once you're in the rotor, once that air is in the rotor, it's really swirling around a lot like a wash machine. It's going to be going up, down, right, left, all directions. It's just going to be tumbling randomly. But the main flow of it is going to be curling up and then down and then back underneath. So it does mix up in all different directions. It's very turbulent. Just like water in a river flowing over a rock in a whitewater river, and you see all the bubbles and all the whitewater churning around just downstream of the rock. It's really mixed up in all directions.
Okay, good. And one final question. What is the maximum wind at the top of the mountain to avoid encountering mountain wave effects?
Generally speaking, if the wind is less than 20 or 25, it's pretty unlikely you're going to get any wave lift or any turbulence or wave off of that mountain range. Now, if it's only blowing 15 and you're right above the treetop level on the back side of the mountain, flying along low level, and it's 15 or 20, yeah, you could get some downdrafts and some really crashy air on the immediate lee side at low level. But when it comes to mountain wave, you know, if it's only blowing 20, 25, 30, it's not blowing 50 or 60 like it sometimes does, then your rotors and your lee side wave is not going to produce that severe of a turbulent condition. So some of the literature I read said wave could form with as little as 15 knots. And I've actually experienced that in airplanes a couple of times where I was, the wind was maybe 15, 20 at the max, and there was wave condition, but it was really weak, and it was smooth, it was rising air, but it was really difficult to work and gain altitude, but you could tell it was waves. So.
Okay.
Really.
All right, thanks. One more just popped up. We'll do that, and then we'll let you get back to work. Can there be a rotor with no visible cloud, dust, etc.?
Yes, absolutely. Yeah, we can get dry wave with no visible clouds, and if there's not enough moisture, you can still get that turbulent flow of air that curls up and around in the rotor. Absolutely.
Okay, sounds good. All right, thank you. I'll mute my mic again and back to work.
Okay, yeah, and so we're going to look at some evidence of aircraft accidents that have resulted from mountain wave. Just by looking at that photo on the right-hand side, this is just kind of a trivia question. That's actually the vertical stabilizer of an aircraft. You can see the rudder kind of canted down, and there's a little window underneath. Does anybody know what kind of aircraft that might be? And this is up in Alaska. The clue is that little window underneath the rudder. That's actually a B-29, just like the one that dropped the atomic bomb on Hiroshima. So that little window, the tail gunner's little window is the giveaway. So that's a B-29 that crashed back in the late 40s, early 50s in Alaska as a result of mountain waves. So. Okay, some of the more well-known or publicized accidents, you know, that have occurred. These are just some major structural failures that have occurred on large transport aircraft that are built really strong. Look at that one on the 747 in Anchorage. When it says the number 2 engine separated shortly after takeoff, and this is from the NTSB report, they say an encounter with severe or extreme turbulence associated with mountain wave. So if it was just after takeoff, I suspect that was a rotor, a strong rotor at lower altitude, as opposed to the clear air turbulence way up high in the braking wave, which is what you would find at 25,000 feet or higher. So that was an interesting one. This is right out of that advisory circular that I referenced at the beginning. They have a whole list of accidents associated with wave and turbulence. So some of these will say, they just have a quick blurb, mountain wave, and here it has plus and minus G's, wind rotor suspected, strong lee wave. So there's a lot of, it can cause a lot of havoc. This is an image that was produced by the National Weather Service. Some folks in Boise and Salt Lake put this together. there is no real ICAO criteria for measuring severity. So the Weather Service folks who do aviation forecasting came up with these descriptors and these adjectives to describe how strong of an updraft or downdraft, for example, speed changes on your airspeed indicator constitute moderate or severe wave. So they really wanted people to stress submitting PIREPs, so it's helpful to pilots at all at flying at any altitude to really hear or understand what kind of effects it's having on your aircraft in terms of speed fluctuations, altitude fluctuations. This is a popular photo from the 1964. This B-52 was actually being flown by some test pilots who had some sensors on board, and they were actually doing studies of the effects of lee side rotors and mountain wave on aircraft. And they were flying north along the east side of the Colorado Rockies, down by Colorado Springs, at about 14,000 feet when they got whacked by this rotor, and it snapped off the vertical tail. And they were able to fly this aircraft for 3 or 4 more hours using some good CRM. They extended that landing gear down to help stabilize the yawing motion that they couldn't control anymore. And they were able to get this puppy back on the ground and land it without that stabilizer on there. Just amazing example of very good CRM that they employed, and use of asymmetrical power adjustments on the engines in order to assist with coordinating turns and things like that. So pretty amazing story due to mountain wave rotor. So rotor clouds sometimes have the innocent appearance of just a little wispy cloud like the one I showed earlier in the Bitterroot, or you can get these roll clouds, and you can, if you look at them, you can actually see them kind of curling around. Again, this is just a graphic diagram of how far downwind from the mountains out of the plains where the initial rotor is found here. Again, picture's worth 1,000 words. This is kind of some other rotor clouds. These, if you put a time-lapse video image, you would see them curling up and around. Again, they don't look like anything really severe or hazardous. They just look like kind of a wispy cumulus cloud, kind of like you see in the summertime when we have thermals and you see wispy cumulus kind of form and then dissipate if you don't have enough moisture or energy to form towering cumulus and thunderstorms. Sometimes you see clouds that look just like this, but don't be fooled by them. This one has a couple of curls underneath it, you can see, with a cap over the top where the wind is actually stronger and shearing off the top of that cloud, making it look real milky in appearance. So here's where we were talking about, tips for flying near mountain wave. Avoid flying lower. This is a general statement. Anytime you have winds aloft over a mountain that's 20, 25, stay at least 1,000 above the mountaintop level, if not higher. And if it's stronger, say it's 50-knot wind at mountaintop level, I'd give it at least 2,000 or 3,000 foot of altitude above the mountaintops if I needed to cross the mountain range. Here we go. This is your 1/2 rule. The base is 7,000 feet. Summit's 11,000 feet. That's a 4,000 foot difference between the base and the peak and the mountain peaks, and divide by 2 and cross over at least 2,000 feet above the top. So in this case, that would be 13,000 feet if you needed to cross over. So here's one that's kind of counterintuitive. A lot of times if I'm flying or pilots are flying and they get into strong sink, their first inclination is to add full power, pitch up, fly at VY, and try and climb and maintain your altitude. But it's really actually better to pitch down, add power, and go really fast and get the heck out of there. The less time you spend in sink and the sooner you can get into a pocket of air that's not sinking, you'll actually lose less altitude than you will trying to fight it with your engine and your pitch attitude. So rather than fly at VY with full power, turn around, get out of there. If you have mountain wave conditions, it's usually going to be on the lee side out over the flat terrain. You're not going to necessarily be over the mountains. Obviously, if you're over mountainous terrain, you got to be careful about turning downwind and flying into a mountainside. You don't want to do that. Always have a way out. That's rule number one in mountain flying. And in this case, remain at or below your maneuvering speed in turbulence so you don't incur any structural damage. So here's another image from a glider in the Owens Valley of flying along the leading edge of mountain wave. So here's some of the factors that soaring pilots need to keep in consideration. If I'm going to go flying in a glider and there's a vertically propagating wave like the one shown in the photo, I'm going to get some really powerful lift off of that, but boy, I better be on my A game because these are major league conditions to try and soar in. Again, the trapped lee waves that are not as severe, they're much easier for new pilots or pilots without a lot of experience in wave to actually soar in. Now, one thing I'm going to say here, this is a personal choice that I've made. I don't recommend this necessarily, but it's something that I've been comfortable doing myself. But again, it's just my personal opinion that when I'm out flying in a Cessna or something, or in a light GA aircraft, and I encounter wave, I like to throttle back to idle, slow the airplane down, put my carb heat on, put down 10 degrees flap, fly it at 60, 65, and try and work that wave and try and gain altitude on it in an airplane just like I would in a glider. And doing that, I've learned a lot. I've learned so much about where to find the lift, how to work the lift, how to soar. And I've been up to some fairly high altitudes, well below Class A, of course, but in Piper Cherokees and Cessnas, I've been able to climb at idle at 500, 600, 700 feet per minute in wave and really learned a lot about that. It's a personal choice. Like I said, you can do that if you'd like, if you have the conditions and it's safe to do so, but just throwing that out there. So one thing I've learned, here's another picture of that wave on the same day I downloaded the weather reports. This was in the Bitterroot Valley, and it pulses and moves. So if I put time-lapse video on that photo on the right, on the left, I mean, you would see that, you know, this wave kind of moves in and out and different parts of it change. It kind of ebbs and flows just like the waves on the beach. So if I were standing here on the beach, one wave might come all the way up and get my feet wet, but over here it might do it 10 minutes later on. I might not get a wave come up that far. Sometimes the wave is strong here, sometimes it's here. It ebbs and flows. And when you think about the atmosphere and the air, we always like to think of air has fluid properties. Here's a classic example. So challenges. Now, if I'm flying a glider, I either have to stay on tow and pay more money to get towed to a higher altitude to find the wave lift before I release. That's not uncommon. Normally on a thermal day, I can get a tow to 1,500, 2,000 feet, fly into a thermal, release from the tow rope and start turning and go up, and I'm good for a few hours after that. I can stay up a long time. But in wave, you got to be really careful because you got to be sometimes it's hard to find thermal lift to get up to the wave, but if you can, that's great. Another hazard for sailplane pilots is sometimes you can get in sync that you just can't escape on the backside, or that you just can't get out of. I've had to land out on the east side of the Rockies there in Montana on the flats on a dirt road in a remote area because I got into 3,000 foot per minute sync and I could not find any lift. Boom, I got on the road, had to call and get my friend to come with the trailer and take the wings up and throw the glider out of there. But, so that's something to take into consideration. Yeah, another issue is if you got really strong winds aloft, sometimes in the Owens Valley, you'll get surface winds 30, 35 knots, and the winds at 2,000, 3,000 feet are 50 knots. If you go 3 or 4 miles downwind of the airport, you're up high at 12, 13,000 feet, you can pitch down. You might not even make it back to the airport that's only 5 miles away upwind if you get in sync. So always have a way out, somewhere to land, and don't get blown back. Cross-country flight and wave is difficult. Normally in thermals is where, in the summertime, your soaring thermals is where you can go longer distances cross-country. Now, when you have wave that is hitting a mountain range and rebounding and getting re-energized up over subsequent mountain ranges downwind, you can skip from one wave downwind to the next one, to the next one, to the next one. And here's an example. I'm going to put my camera back on just for a second. Okay, this is an article from 2011 in Soaring magazine about a guy that flew 2,200 miles in mountain wave, and he stayed up for 13 hours. So here's a kind of an exception to that rule where you can fly longer distances downwind in mountain wave or up and down a mountain range on the lee side and work that lift and go long distance. But generally speaking, if a glider pilot wants to go cross country, it's easier in the summertime with thermals. Okay, let's see here. All right, let's talk about some of the other hazards. What can possibly go wrong? Hey, at higher altitudes, you need oxygen, not only for the federal aviation regs, but just to keep yourself conscious and alert. If you're going to go up, shooting up past 13, 14, 15,000 feet, oxygen systems have to be checked and tested, and they can fail. So got to be super aware if your oxygen's getting low or if the system is icing up or something. Canopies can ice up. There have been glider pilots who are suddenly flying in what looked like IMC simply because the frost formed on the inside of the canopy. Cold temperatures, got to dress for that weather. Other traffic in the airspace. We're going to talk about wave windows or waivers that allow people to fly in Class A, but that's something to think about. At high altitudes, you'll get high-speed twins and jets and all kinds of aircraft flying. Rotors, turbulence, we talked about that, resulting in a forced landing out. Bottom line, always have a way out. All right, so this is a big one too. It is possible if you're in really strong winds that you could be backing into a lenticular that's behind you. You got to be looking around and super vigilant about, be very careful, always have a way out. There's a photo coming up that will show that. If you go inadvertent VMC flight into IMC, gliders don't have engine-driven vacuum pumps and gyroscopic instruments. You can get disoriented and upside down so quick in a glider, and there have been fatal accidents where spatial disorientation resulted in loss of control and in-flight breaks up because VNE was exceeded. So those are some issues. Here's a perfect example of this. Here you have rotor clouds underneath, you have wave above, you have this guy flying along, and you know, there's a lot of moisture in the atmosphere. So this pilot is really thinking, okay, I'm working the lift, I'm trying to go up, but boy, if I go up too high, look at it, solid overcast, but with wave above, and you know, it's kind of a scattered to broken layer underneath. There's not a lot of big holes other than the one right next to them to descend through if you have to. It's a real cat and mouse game, soaring gliders, to say, can I make it over to that wave? Look at that wave over there. The guy in the picture on the right said, boy, there's some wave over there. If only I can get high enough. This is at Hood River, Oregon. I need to gain some altitude, clear that terrain, find a thermal and go up, and then shoot across the Columbia River here over into the state of Washington to try and find that wave. So where he's at right now, almost eye level with some low hills, he's got a lot of work to do in order to get to that altitude and make it over there. But those are the kind of things you got to keep in mind if you're going to go fly in mountain wave. Do you have your logistics in place? Well, if I land out somewhere and I don't make it back, do I have somebody ready to go with my trailer, and do they have the keys to my vehicle and the tools needed to take the wings off my glider and stuff. And you don't want to just go over there just because it looks great, but sometimes it's really tempting. So we talked a little bit about flying in Class A. This is an area north of Sacramento, California, kind of up towards Napa Valley. There are several places in the country where soaring clubs have a waiver with the FAA, and there are certain rules and procedures you have to follow. Got to call up ATC at least an hour in advance and say, hey, I'd like to activate the wave window. I'm planning to be possibly above 18,000 feet between 1 p.m. and 4 p.m. this afternoon, and there's several, and you have to call them when you're back down out of the wave and down at your airport again. But they do exist, and there's strict rules to follow. But you can fly gliders in Class A without ADS-B and without a transponder if you have a wave window in place. So here's some altitude records. We're getting close to the end here. State record here in Montana, 35,000 feet, set way back in 73. National record here in the U.S., 49,000 feet in Owens Valley. That's pretty good for a glider. And the world record is, does anybody know about the Perlan project? This is a project that is ongoing, a multi-year project by some well-funded researchers flying this high-altitude glider that's pressurized. So far, they've gotten to 76,000 feet over the Patagonian Andes in South America, Argentina. Their goal is to reach 90,000 feet sometime in the next couple of years. So this is the current world record in a glider in mountain wave. Pretty amazing. It's a pressurized glider, and you can go to their website, Perlan Project, and Google that and read all about it, and they've got some videos on there. So my final recommendation for any powered pilot is, man, if you can get your glider rating and start soaring, it teaches you so much about the weather and about airmanship and good rudder coordination. It is just phenomenal skill. And boy, I tell you what, if you're like me, you're going to get hooked, and you say, you know what, if I don't fly power airplane ever again in my entire life and I could only fly gliders, I would be so happy. It is just really, really fun. So highly recommend getting some glider time, even if it's just thermaling with somebody in the summer for an hour or two. Really great experience and a really fun rating to add to your pilot certificate. So that's all I had. Layne, do we have any more questions? This is my contact information if anybody needs to email a question to me.
Kurt, I'm not seeing anything, but Gene might be able to.
Yeah.
Okay.
We've had some issues with Layne being able to see the questions, and I'm not sure why, but we have one more. Oh, no, I guess some more just come in. Bear with me here. They put this in about a 6-point font, and guys might have a little trouble with that. Anyway, this one says, any thoughts or comments on the Steve Fawcett crash?
I have some thoughts about that. I would have to pull up the actual NTSB report to see what their conclusions were, but clearly that was a day, high-density altitude day, low-level flying on the lee side of the Sierras, and obviously the aircraft he was flying didn't have a whole lot of horsepower, so quite likely he got into some sinking air, whether it was mountain wave or just lee side rotor from air flowing up and over the backside of the train, probably got into some sinking air that the aircraft didn't have enough power to outclimb. And that's the bottom line, I believe, what happened there. Okay. But again, I look at the NTSB report to determine that. But that's not an uncommon cause of a lot of mountain accidents up and down the Rockies, the Sierras, and the Cascades. Underpowered aircraft flying into air that they were unable to outclimb. because it was sinking or it was a rotor or a downdraft.
Okay, thank you. There are no more questions, but there's two comments here that you might enjoy. The first one says, excellent presentation. I live on the east slope of the Cascades in central Washington. I learned a tremendous amount about clouds I see, and I will respect them even more. The other one just says, outstanding presentation, great information, thanks. And that's all the questions that we have there. So that's great. Great job. We appreciate that. And let me go back to my webcam here again. There we go. Okay. I think I'm going to have to mute right now because we're getting feedback. There we go. We can open you again later, Kurt. But I want to thank Kurt for that presentation. That was really outstanding. And I'm going to take being presenter back and show my screen. And hey, what do you know? It worked. Love it when a plan comes together. All right, anyway, especially I do want to thank Kurt for taking his time today. And it wasn't just the time today, but we did a practice session on for the Zoom platform. And then, of course, when that flopped out yesterday, we scrambled to do a practice session on the GoToWebinar platform. So made Kurt kind of a busy guy here, and we really appreciate his expertise in here. As a Flatlander pilot, the mountain flying is something that I don't know about. As I told Kurt jokingly earlier, my solution to mountain flying was going over 30,000 feet and commenting on how pretty those mountains were down below me. So we appreciate that. That was great. All right, in case you didn't know, Avemco offers a safety rewards program. Attendees at this event or any of the other events, or those who take any safety-based education courses, can receive a percentage off their annual Avemco premium at the time of the quote or the renewal. All you have to do is ask, just let them know, and they'll take care of you. Okay, we just recently added 2 new events. When I say recently, I'm talking about an hour and a half ago. We have added 2 new events to our Avemco webinar series. These presentations involve some need-to-know information regarding aircraft engines. Both these presentations were scheduled to be presented at AirVenture this year, but since it's been canceled, we were able to bring them into our series. They'll be presented by Gene Benson, who has presented aircraft engine programs several times, both AirVenture and Sun & Fun. Registration links for these can be found on the vectorsforsafety.com website in the Pilot Talks section. And of course, those will also be recorded for later viewing. Please visit our website, vectorsforsafety.com. We have links to videos and to online courses. All but one of the courses is free. There's a link to a 50% discount on the one that is not free. Most of our webinars in this series have been recorded. They can be found in the videos section on that site, on the Vectors for Safety site. And from on that site, you can also join our mailing list to receive the monthly or a little bit more frequently sometimes Vectors for Safety publication, and that will be coming out, of course, on June 1st if I hurry up and finish writing it. So thank you all for attending. We appreciate your attention on these, and I want to especially thank Kurt and Layne for joining us today and for participating and helping us out, and it's really a great function to it. So thank you all for that. And like I always sign my emails, we'll close by saying, please remember, always fly like your life depends on it.